this wonderful series of lectures. And with this word, I now hand over to JD to introduce Greg.
Sorry. Hi. Okay. Well, let me again warmly welcome Professor Greg Engel from University of Chicago, and it's a pleasure to introduce him because he has been a sort of a leading exponent and pioneer in the community, and it's always great to follow his papers, and I and my group have been sort of looking at what he has been doing. So Greg actually got his AB degree, as we call it in Princeton, in 1999. So he did an undergraduate there. And then he moved to Harvard and worked with Professor James Anderson and finished his PhD by 2005, where he pulled up some, worked on optics and other kinds of very interesting experiments in Professor James Anderson's lab. But what was interesting is he made this transition to University of California, Berkeley, where he worked with one of the pioneers in ultrafast community, Professor Graham Fleming, and he came up with this sort of a field opening paper in Nature in 2007, where they reported for the first time that there could be a possibility that electronic coherences could sort of dictate energy transport in photosynthesis. And that paper really sprung open a new community, a new field called quantum biology. And Greg has been a proponent of that for a long time. He has been an independent professor now for almost 13, 14 years at the University of Chicago. He's a full professor there. And he has been advocating this idea, doing the most important and the cutting edge experiments, setting up equipments to follow this in greater detail and discovering new things about this idea. His work has been sort of rewarded. He actually won all the young career fellowships. Basically, his Berkeley position was a Miller Fellowship, which is also a very, very reputed fellowship. Only few people in the States get that. And post his, as an independent PI since 2007, he actually got the Camille and Henry Dreyfus New Faculty Award. He was named as Scientific American's Top 50 Leaders in Research. He was the AFOSR Young Investigator Program. He was awarded a funding from there. He was a Searle Scholar. And more recently, he has been given the Young Scientist Award from the World Economic Forum. And of course, I can mention a lot of very interesting awards. One of them is the Dreyfus Teacher Scholar Award, as well as the Llewellyn John and Harriet Manchester Quantrill Award for undergraduate teaching. So not only in actually setting up a world-class research program in Chicago, he has been sort of driving students to do fantastic research through his scholarship and teaching. So, Greg, it's our honor that you have joined us for this teaching sessions, and we are so very happy that you are so humble in all these things, and you are giving us your absolute insight in what you think about this field. So, thank you, Greg, and you can start yourself.
Thank you very much, Adi. I appreciate it, and it's my pleasure to be here. I hope you guys can see the slides. I'm going to try to get rid of that black box that we had an issue with yesterday. So let me know if there are problems with it.
No.
But I really appreciate the opportunity to come here, virtually at least, and speak with you and tell you about our science. So yesterday, I talked a bit about 2D spectroscopy and how it was built and what some of the information content is, and tried to set up some of the problems that we will answer or move towards answering a bit today. And at the end of the talk last time, I showed you a lot about coherences, these little wiggles that you see, and how they come from what would be in a wave function picture, a superposition of states, or in an ensemble picture, coherences, and how this led to a lot of ideas and a lot of questions. And I'll pick up with those ideas in this talk. And I'll take a small jag to the side at JD's request to go through a bit of the fundamental physics behind the nonlinear spectroscopy and the Feynman diagrams. So for those of you who have taken a lot of graduate quantum mechanics, you'll have to forgive me for the few-minute jaunt back in time as you first saw that. But we'll pick up from the beginning and go quickly through some of that to bring us all the way up to nonlinear spectroscopy, sort of from first principles. The topic I really want to speak about today is tuning vibronic coupling to affect energy transfer within a photosynthetic complex. So at the end of the last talk, we were talking about light harvesting and how you think about going out and grabbing that energy from the sun and using it. And our comment was that biology has been doing this for a long time, and we can look to biology for design principles. And when we did this, this is what led us to see those coherences in our signals. But the big question is, what do they mean? Are they real? And just to remind people of this problem and what we were working with, we're talking about these green sulfur bacteria that live in the microbial mats, these ones that receive very, very low light. So they have evolved to be efficient. There are a lot of things that you could imagine being necessary for survival. If you think about trees, photoprotection is it. They get hit by really bright light, they get shaded, and then the shade moves away and it comes back, and they have to very dynamically change their light harvesting. These little bugs don't have that problem. They live in the worst environments you can imagine. They're relegated to the bottom of the Black Sea, to the bottom of this inch-thick microbial mat. These guys don't worry too much about photoprotection. They never see bright sunlight, but they do worry about efficiency. When they absorb that photon, they want to pass it to the reaction center without ever dropping that quantum of energy. And so that's what these bugs do. They're highly efficient and they absorb the light. But when you live in a pile of mud or microbial mats, there are things that worry you. These guys have to worry about someone stepping in their pool. They have to worry about having their mud stirred up. They have to worry about oxygen penetrating down to wherever they're sitting in that layer of mud at the bottom, because they are anaerobic organisms. And so oxidative damage is something that worries them. I mean, as much as you can worry a bacteria, please forgive the anthropomorphizing, but I think it makes it a little easier to understand what's going on. And so these bugs are trying to harvest light from the sun. They have a doubling time of 22 years, which is roughly the same as ours. And they just live on the very bleeding edge of being able to survive. These are some of the most ancient photosynthetic organisms. And the way they do this is they have this Fenner-Matthews-Olsen complex, which is the linker between the main antenna and the reaction center, and the energy passes through it. So here you see all of the bacterial chlorophylls there. If we just look at the chlorin rings, the part that contains the transition dipole, they look like this. All of those different transition dipoles coupled to one another through dipole-dipole coupling. And then we can diagonalize that Hamiltonian. You see these slightly delocalized states. And some of these are really quite localized, like exciton 1, but others like exciton 2, where you see just a little bit of orange. That's because it has a component on about 4 or 5 different chromophores. The other one I will call your attention to is the green one in the middle, exciton 4. And I'll try to show you these in different ways, but most of the talk today is going to be about those 3 states, exciton 4, exciton 2, and exciton 1. And we're going to go look and try and understand what's going on with these organisms and how they work. So these are the pathways I showed you last time that Tobias Brixner extracted from 2D spectroscopy, what I would call the main pathways. And you have this sort of 4 to 2 to 1 pathway. There's also direct transfer from 4 to 1, which was not shown in his diagram, but it actually turns out to be quite important. And now I'm just going to step back to the very beginning. So those are the bugs we're going to look at. That's the problem. I'm going to come back to your first day of quantum mechanics at JD's request and talk a little bit about what happens in our spectroscopy. So here is the time-dependent Schrodinger equation. Very simple. The time derivative of the wave function is related to the Hamiltonian. That is to say, it's the Hamiltonian that determines the time propagation. And that's the part I really want you to get, because later when we just let the system evolve in time, what we're going to be measuring are properties of this Hamiltonian. So it comes directly from this equation and is pretty clear. But we also want to think about light matter interactions and coherences. So what do? Well, your second lecture in quantum mechanics is going to be going down to h psi equals e psi, the time independent version of this equation. Very, very simple. And I just want to call your attention here to this e to the negative iet over h bar term. That's the one that causes oscillations. That's what's going to cause macroscopic electric fields when you have electron clouds moving up and down in a concerted fashion. That's what you do when light interacts with the system. Say you shine a laser on it, and it's what happens when light comes out of a system and you wait for that photon echo. It's that e to the negative iet over h bar that's going to drive all the physics that let you pump and probe these systems. So let's just think about what happens. We'll go to a hydrogen atom, something familiar to chemists. Here's a 1s orbital and a 2p orbital of a hydrogen atom. Nothing new here, I hope. The plus and minus are for phase, obviously not charge, just in case people are worried. And I want to think about what happens when light hits this. Let's take a femtosecond pulse and look at a hydrogen atom in a 1s state. So what is the femtosecond pulse? It's a few cycle pulse, depending on the width of it. And it's an oscillating E field that oscillates in both space and time. So if you're an atom and you're just a point in space, you're going to see this E field sweep across you. And what happens? Well, there's a nucleus there, it has positive charge, and there's an electron that has negative charge, and that's what that orbital is. So as that E field sweeps across, it starts to pull the electron and proton in opposite ways. Proton's heavy, so you basically just see the electron move, and it leads to this oscillation. And that oscillation is a coherence. And the reason you get that oscillation and that coherence oscillating at exactly that frequency when that light pulse comes flying through and excites this thing is because of that e to the negative iet over h bar. What does this superposition look like? Pretty simple. You started out in a 1s, you do your time-independent perturbation or time-dependent perturbation theory, and you're going to find that you get a probability that you're still in 1s. That, of course, happens. You don't excite everything. But you also get a probability that you're now in 2p. And that oscillation is this energy gap difference between 1s and 2p. And that's precisely what causes that, that oscillation. And if you think about what it looks like, if I go back one slide, let me try and go back and play the video. What this is going to look like is a superposition of 1s plus 2p and 1s minus 2p. And that's how you offset the cloud to the top versus the bottom. It's a lot like creating sp orbitals in your organic chemistry class, but they oscillate back and forth because you have an oscillating E field. Now you can imagine if while this thing's oscillating, we put in a second pulse, we could stop that oscillation dead in its tracks. Then we would create a population. And that population could be in the excited state, or it could be in the ground state. You wouldn't necessarily know, and in general, in fact, it would be both. And then, of course, you can send in a third pulse, because why not? You've got lots of laser pulses. And then you could create a new coherence that might teach you something about the system. And that's, in fact, what we're going to do. So our spectroscopic strategy is that we always look at coherences. And those coherences just come from that e to the negative iet over h bar, which comes precisely from, instead of looking at a wave function, we look at a density matrix, the Hamiltonian operating on the left and the right of the density matrix. So we're going to keep track of these density matrix terms by looking at the Hamiltonian, squeezing them from both sides. And if you think about a wave function and a superposition that I was showing you before, what that translates to in this formalism, when you have an ensemble of states, that superposition character is what we call a coherence. So when you have just one particle where you know its wave function, you can have a state, say a time-independent state psi, or you can have a superposition psi1 plus psi2. But when you have an ensemble, you might have some in psi1, some in psi2, or you might have them all in superpositions between psi1 and psi2, and you have to express those things differently. That's what the density matrix gives us. It lets us move from a wave function of a single particle to an ensemble. And if you think about a Boltzmann ensemble or something like that, you'll need a density matrix to express that quantum mechanically. And so that's what we do here. But still, the Schrodinger equation sits in the background. The Schrodinger equation tells you the time dependence, and it should come as no surprise that you get this I over h bar term and you get a Hamiltonian term. All of this comes directly from the time-dependent Schrodinger equation. And then you have another element to this, which is that all of these molecules are in little different environments. And while they all may start out in phase and they all may be oscillating phase at exactly the same speed, every once in a while, one of them gets jostled and the speed changes until you get cancellation. And then your field disappears. And that's what this relaxation due to the environment term is. It's a dephasing term that causes you to lose the ability to see a coherence. Because otherwise, when light hits one of these, you will get a coherence and an oscillation that would continue forever. But of course, that's not what you're taught in general chemistry, is it? What you're taught is that when you shine light on it, you'll see some excited states and some ground states. Some will have absorbed the light, not that everything is in a superposition. And that's because your general chemistry professor waited more than a few hundred femtoseconds to give you the answer to the problem. So when light hit it, it was a coherence, but that thing dephased into a mixture of excited and ground state within a few hundred femtoseconds, and the professor didn't care much about that first few hundred femtoseconds. So just told you have a mixture of excited and ground, and that's what excitation is in a typical freshman chemistry class or even an early graduate class. Here, however, where we care about those short timescales, we've got to watch the coherence. That's our observable. And so we can propagate this in time. The energy gap is going to be the frequency that we see. That's true of any spectroscopy. The frequency that you excite always has to match the energy gap between the states. And the line shape will have to do with the environment. And this gives us these types of signals that we see, whether it's a photon echo or a coherence during the waiting time. They all have this character where the light that we see comes from an energy gap in the oscillation, and the line shape we see tells us something about the environment. Now, how we keep track of all of these is a stroke of brilliance from Shaul Mukamel and, by extension, Richard Feynman, and that's using Feynman diagrams. So when you look at this diagram in the upper left, think of time moving from bottom to top. So the first pulse comes in, and then what you get is a coherence where the bra state is still in the ground state, the ket state is still in the ground state, and the bra state is in the excited state. And so you get a GE coherence, and that's an optical frequency. The difference between the ground and the excited state is an optical oscillation. That's in fact exactly the frequency of your laser for the color of light that was absorbed. After the second pulse in this pathway, you have an interaction on the other side, which brings this G up to an E, and that stops that oscillation dead in its tracks. This is like watching that hydrogen atom where I was pulling on the electron cloud, and then having an oscillation that comes in exactly out of phase and stops that oscillation dead in its tracks. And then I'm going to be a population in the excited state. There would be another perturbation theory term where I'd be in the ground state, but we'll come back to that. The third pulse will come in, and it will take this thing that's not oscillating and start it oscillating again. And that gives you another coherence between the excited and the ground state. But look here, there's something very interesting. This one was GE, this one is EG. What that means is the sign of this e to the negative IET over h bar or e to the positive IET over h bar, because they're complex conjugates, whether it's acting on the left or the right, they're opposite sign. So one of them winds up the phase and the other unwinds the phase. Now, what this means is that you can get back to where you started. You get an echo. So if JD and I went out for a race around the track and he's much faster than I am, we might both start running at the same time, but he's going to go farther than I do. But then we stop and we turn around and we run back. Well, he's still faster than I am. So we're going to get back to the starting line at the same point. He may have gone 400 meters. I may have only gone 150. So what? We're going to end up at the starting line at the same time because I only have to go 150 meters back and he has to go 400 meters back. And what that means is when you wind up the phase, you wait a little while and you unwind it, you can get a macroscopic E field where the entire system comes back into phase and emits a pulse of light later. That's the photon echo that comes out as the signal. And the only rules that you have here are that your final state has to be a population state. And that comes from the fact that you get information out of a density matrix as an observable in quantum mechanics from the trace of the density matrix. So you start out typically in the ground state when you talk about electronic spectroscopy. You can tickle this thing on the right to get a GE coherence, tickle it on the left to get an EE population, tickle it on the right again to take a little energy out and get back to an EG, and then you'll get an emitted signal, a photon echo. Now, you also can rearrange this in all possible ways. you could imagine interaction on the left, and then another interaction on the right, another interaction on the right, and a third interaction on the right. All these things can happen and are perfectly fine. So there are lots of different ways to build up these diagrams. And in general, you have to take into account all of them. So last time I showed you a few. This one that goes through the excited state. Here's one where during that middle time, I have two different excited states. What that means is I'm going to see an oscillation in this waiting time in the middle that wasn't there before. This e to the negative iet over h bar term comes from the energy gap difference here. And the difference between E and E prime is going to be very small because they're both bacterial chlorophylls. They just have a small gap between the two states. It opens up because of the coupling. And now what you're going to see is a very slow oscillation, not the optical frequency where you get one cycle every 2.5 femtoseconds or every 2.3 femtoseconds. Instead, you're going to get a cycle every 100 femtoseconds. So it's going to be a 50 times smaller gap. It's not the difference between 0 and 12,500. It's a difference between 12,200 and 12,500. And so this oscillation will be very slow. That's the one that we talked about in the last talk yesterday. And you can imagine building these up in all possible ways, using all the states that are available in the system and all the possible patterns. And as long as you have an EG coherence at the top and here a GE coherence at the bottom, these are called rephasing pathways because they wind up the phase one way and then they unwind it to put it back to give you a macroscopic field. That's a photon echo.
Greg, there's a question. Greg,
Yeah.
Ravi, you want to ask a question?
Yeah. Greg, I mean, it's a really nice description actually, and I was just wondering, maybe you should. It would be great for you to, we could have a comment on phase matching, because the way you actually get these particular coherences lined up in this way is by controlling the phase of the input pulses in this case.
Yes. Okay. So this is very true. Let me get to that in just a moment. I think you're absolutely right. That is how we implement this experimentally. And let me say something about this one first, and then I'll get to that. If you have a pathway like this, where you have an EG coherence on both sides, you get what's called free induction decay, which is to say that you wind up the phase and then you wind it up more. And so this is like that lens picture at the bottom where the phase spreads, and then after the third interaction, it spreads even more. Now, I think it was Ravindra's point is very, very well taken. When you have lots of laser pulses, and the first three of them are really strong, whoppingly large pulses, and then that last one, that signal, is really tiny, you have a few choices on how you're going to see that signal. One is to look for a small difference amidst a large background. And you can do this, and this works. It's what NMR does, and they have to do it. And that usually requires phase cycling. That is, you have to control the relative phase of pulses 1, 2, and 3. No problem at all. You can do that. It's just hard. And then you can figure out how those little changes manifest in the signal as you try and cancel the very large background. But we have an advantage in the optical regime, which is exactly what Ravindra said. It's called phase matching. That is, that these pulses carry enough linear momentum that you have to conserve momentum through this interaction. So if pulse 1 and 2 come in from different directions, and then pulse 3 comes in from a third direction yet, you can arrange it such that the signal comes out in a unique direction with zero background. And that sounds really good until you realize you need to heterodyne detect it. So you need to add a tiny little local oscillator in that known direction so that it can mix with that signal, and you can actually have the two pulses used for detection that I showed you in the video in my last presentation, where the pulses all came in from different directions and the signal in the local oscillator came out in a unique direction, which I then filtered with a piece of metal. I didn't put the video back into this talk because I showed it to you last time. I probably should have, so you can see how that works. But you're absolutely right. So you're given a choice between phase cycling, which you can do with SLMs and gradients, and this is pioneered by Keith Nelson, among others. Or you can go with phase matching, which is much, much easier and gives you a zero background experiment. You can actually combine the two, which Keith has done as well. And this is interesting. So the phase matching is a necessary thing, and it comes from all of these K vectors, these wave vectors, actually being vector quantities. And that's because your wavelength is short compared to the width of your sample. Even if you have a micron long sample, millimeter long sample, you have a micron long wavelength. And so you end up having directionality in all of these different signals. And it turns out that if you're very careful and you do this even on a 2D material, you can work out that the same thing happens without the need for that deep sample, but it's not quite as obvious at first why that is. So the photons conserve momentum, the interaction conserves momentum. That should be obvious. And that's something that we can exploit experimentally in the lab. It's not necessary, though. I would point out that Shaul Mukamel will tell you that you can get nonlinear response from single photons, albeit rarely. And so you can use the same laser pulse to do all of these interactions. It's just very hard to see your signal. So some people will use a pump probe geometry where K1 and K2 are degenerate, in which case the signal comes out in the direction of your probe and is self-heterodyne. That has both advantages and disadvantages. Dynamic range is hard, but phasing is easy. So there are lots of different ways to implement this. The Feynman diagram doesn't really tell you how to implement it, but it shows you the tools. You have a phase-sensitive measurement, and you have 3 different K vectors to play with to determine that final K vector of your signal. And that gives you the phase matching or the phase cycling options as you build your spectrometer. And you can mix and match and play a lot of different games with this. You also can think carefully about polarization and orientational factors so that you can cancel out certain terms where different dipoles might point in different directions. E and E prime may not be parallel, and in general, they're not. And then you can play games with your polarization of pulses 1, 2, and 3 to try and isolate those signals where the 2 transition dipoles are parallel or where they're perpendicular, or play around with it to try and measure the angle between the 2. You can get chiral signals this way as well. You can eliminate all dipolar signals and only see chiral and quadrupolar signals. There are lots of fun games that you can play with this. And there are lots more that you can play here than you ever can with pump probe, where K1 and K2 are the same laser pulse, and K3 and your signal have to come out in the same direction. Once you break the symmetry of 1 and 2 coming from different directions, you can go from pump probe to transient grating. When you break the time of K1 and K2, you can then go to photon echoes. There are a lot of different ways to think about how you get information out of these. But the Feynman diagrams are always going to be the answer of keeping track of all the pathways. And if you're an ultrafast spectroscopist, you think about these things in terms of the Feynman diagrams, and those are the diagrams you use to build your spectroscopy and to build your analysis and to build your simulations of your spectra. So they're crucially important to make sure that you obey the laws of quantum mechanics and you keep track of all the perturbation theory terms as you go through and try and understand what your signals are. And one convenient way to think about this is every signal on your spectrum is actually an interference between at least 2 Feynman pathways. And that's a very good way to think about it. So sometimes when you see nothing, it's because 2 Feynman pathways cancel out completely. And if you have a coupling, that cancellation moves because they come out at different places or they have different intensities. And suddenly you see a cross peak show up. And so you keep track of all of your spectroscopy through these Feynman diagrams. I admit this can get a little heady. This is why I left it out of that first talk for a more general audience. But I want to give it to you in a little bit more detail here. And you can go very deep into this. But the diagrammatic expansion is the right way to think about this.
So quickly, Greg, yeah, sorry. You finish your sentence.
No, please.
Okay. No, quickly, I just wanted to say that there are implementations of the 2D electronic in various labs in different ways. And one of the ways you mentioned is the collinear K1, K2. They use the pulse shaper to generate the phases and the pulses, and they separate the pulses out in time. And it becomes easy because you can implement the phase cycling principles quickly, I guess. So is that something that you also like, or you do it in a slightly different?
No, so we use a boxcars geometry or a modified boxcars geometry in all of ours. And we do that because typically with these signals, our signal is so small compared to our probe beam intensity that we quickly run into an issue with signal to noise if we try to see it inside our probe beam. So with really robust samples or dense samples, especially material systems, you can do that very, very well. Yes. But when you get to molecular systems, your signals tend to get much, much weaker. And then if you use a very weak probe, you lose a lot of intensity And if you use a strong probe, then you need massive dynamic range. So we typically use single photon counting detectors. And by going into a boxcar's geometry, we can have a local oscillator that's extremely weak. Now, I would note that people have been very clever. Jennifer Ogilvy came up with a very neat way to play with polarizations, where you can ensure that the signal is in a different polarization direction than the probe, which means that you can then tick the probe 2 degrees off of vertical, so it has a tiny horizontal component, and then you can actually get the best of both worlds if you have a really good polarizer. So there's a lot of room for cleverness in how you build these and how you work around them. And I want to be very clear about that, that this is the playground that ultrafast spectroscopists play in. And so when you look at these and you find a problem like that, you ask, why don't I do it that way? I can explain why I don't do it that way. But then someone like Jennifer can come in and she can say, well, maybe you should do it that way because she's come up with this really good idea.
Right.
And in fact, I have some people in my lab trying to implement that idea of hers now. But anytime you come up with one of these are not fundamental problems with the physics. These are problems with the implementation that can be engineered. And every engineering choice is a compromise. When you gain something, you give up something else. And you have to play with those compromises to try to get the particular data that you're going after. And so there are advantages and disadvantages to every one of these setups. There is no silver bullet, best ever type of setup. They all have pluses and minuses, and you optimize those for your measurement.
Thanks.
Yeah. And that's why I actually wanted to separate the theory of what's happening from Ravinder's very good question about the phase matching, because you don't have to do it that way. We do, and it's really critically important to how we do it. But it doesn't have to be done that way, and others choose different compromises. But the underlying theory in that Feynman diagram is non-negotiable, and that's what's given to you by the quantum mechanics. That's what you have to
just to add, Ravindra actually did his PhD with Shaw. So
then this is not news. I apologize. I was not aware. Yeah, no, there's a lot of cleverness that can happen, and in fact, our chiral spectroscopies were predicted by Shaw Mukamel's group, and there are a lot of cases where we are just picking up the breadcrumbs that he leaves behind, but the devil is in the details. These are not easy experiments to build, as many of you know. So are there any other questions about the Feynman diagrams or the underlying physics or the phase matching or the nonlinear response that people want to ask now before I kind of jump back into the story I was going to tell? This would be a good time if something's not clear to jump in.
Questions, guys? Questions? Okay. Well, I guess we will have it at the end. So
yeah, we can ask again at the end. But thank you. So at the end of last time, I showed you some of this data, looking at coherences. And these coherences that we see in the Nature paper I mentioned, I showed you this data from 2007. There was a subsequent Science paper from the Fleming group by Ho-Jae Lee, also in 2007. An early paper from my group in PNAS in 2010, looking at these oscillations. There's a paper from Greg Scholes seeing somewhat similar oscillations in cryptophyte algae, also in 2010. Those two were published within months of each other. And then importantly, the reason that all of these things took off and actually got legs and created a lot of buzz in the field was early theory from Alana Spuruguzic's group and Martin Plenio's group, among many, many others. But these were the first two through the door around 2009, saying that, this actually could be useful. This could change the way we think about energy transfer in these systems, which is something that we said in our first two papers in 2007, or my paper and Ho-Jae Lee's paper in 2007. There was something here, but we didn't have it fully fleshed out. We had the right idea, but we didn't have the right details. I think in the 2007 paper, I said that this was akin to Grover's algorithm. Alam proved that it was in fact a quantum random walk algorithm, which differs slightly from the search algorithm, but the same type of approach, and that there would be an opportunity for better efficiency because of this. Now, these are taking for granted that we've properly assigned these coherences. And what I like about this is while there will be papers that challenge these assignments, and I don't want to give them short shrift, I'll enumerate them in a little bit, ideas are coming out of this. And in fact, Alana Spurguzic's environmentally assisted quantum transport mechanism has now been implemented on a 10-qubit system in Austria and tested, and in fact, it works. So the real continuous time quantum transport algorithm that Alon invented effectively to explain the data that we see in photosynthesis does work on trapped ions for a 10-qubit computer, and it's real. It's whether you think my data from 2007 assigned it right or not, the idea that it's seeded from Alon has now been implemented and does work. So the good news here is that we are borrowing design ideas from nature. And now the question becomes, well, so is it right or is it not? This is really controversial. I think that 2007 paper has been cited roughly 3,000 times. And I would say about 2,000 of those agree with it, and maybe 1,000 of those disagree. Maybe it goes the other way. Either way, there's a lot of agreement. There's a lot of disagreement. There are a lot of people using it as a jumping off point for other ideas and thoughts. And I think this is exciting. But there are a lot of open questions. And these 4 papers were some of the early ones. There have been many others. These have been seen by many other groups, not just the 3 cited here. But I want to kind of give you a little sense of the background. And then there are a lot of questions. So I've mentioned this paper a few times from Vivek Tiwari and David Jonas, saying that this isn't the right assignment. It's a really cool paper. I should say that clearly. But one of the things that this paper says pretty clearly is they are supposing that our signals are really from ground state vibrational coherences, but that those ground state vibrational coherences come from a mixing on the excited state because we're near a conical intersection. And so there's a non-adiabatic coupling that mixes electronic and vibrational character, and then a particular type of vibration, an anti-correlated asymmetric vibration, can drive that mixing. And that's what gives you these ground state signals, meaning that the ground state signals still report on excited state mixing and dynamics, but themselves may be on the ground state. This is actually, theoretically, it's beautiful, but it's a somewhat complex model. I may be giving it short shrift, but since you have Vivek, you can ask him about that later. There are other models that are a little bit simpler and easier to explain. This one I mentioned last time came out from Martin Plenio. There's a contemporary model that I'll mention in a few minutes from Alexandra Leah-Castro. But this idea that the gaps between the excitonic states match the vibrational gaps is the basis for Tiwari and Jonas's paper suggesting that we're really seeing vibrations. Here, there is a different notion that biology has actually evolved the couplings and the geometric arrangements precisely to match those gaps. So as you relax from one electronic excited state to the next, there's always an attendant vibration to make up the energy gap difference. So this idea that you can go from one excited state to the next simply by leaving behind one vibrational quanta of energy can make this a much more efficient energy transfer process. So now we have 2 different pictures. One saying, look, these are ground state vibrational coherences that report on excited state dynamics. This other paper saying, no, the excited state dynamics are matched to the vibrations, not because you're seeing vibrations, but because you need that vibration to allow dissipation as you relax down that energy ladder. And then, there are papers by Donato Sigmontis trying to pull apart and identify these different coherences. And then, the paper from Tomas Monchal saying, no, you don't want to separate vibration and electronic. These are so tightly mixed that everything is vibronic and you're unable to distinguish the two. And this explains what's going on, which is sort of a hybrid model of the other 3 papers that I just mentioned. And then you get to some of the really interesting ideas from Alexandra Leah-Castro saying, what's happening here is really highly non-classical. That a lot of these mechanisms don't actually go deep enough. And you need to think about the non-classicality of this. And this both means that the vibration itself is quantized, of course, but she also talks quite often in her series of papers about things that go beyond the classical limit, which is very interesting. We don't have strong evidence of that at this point, but I think that's exactly the right kind of supposition that we need to think about how to test. So these are a number of sort of leading ideas in the field. And what I want to tell you, and it's not exhaustive, by the way, I've given you 4 of maybe 1,000 different papers in this space, but they're 4 of my favorites.
And what about this paper from Dwayne's lab, 2017 PNS, where he says it's 60 femtoseconds and
yeah. So no, it's I will get to that shortly. I'm not highlighting it here, but I will try and tell you how you switch on and switch off these effects.
Okay.
And this I think actually settles a lot of these questions in the field. But we'll see. I mean, time will tell. So what I'm trying to say here is this is controversial. And there are measurements by Zygmontas and by Miller suggesting that the electronic coherence goes away very fast and everything that's left is vibrational character. Then the other breakthrough that I want to tell you about is something that we have been waiting about 35 years for, but Bob Blankenship and his team finally did. They got genetics in these organisms. So even though molecular biology is an older field, all of these photosynthetic complexes have to be grown in the native organisms. It's very hard to make mutants in these green sulfur bacteria because they're obligate phototrophs. They have to live on the light. So if you knock out the photosynthetic complexes, they're all dead. And so you have to find ways to switch on and switch off those complexes that are expressed. So in essence, you have to grow them and then be able to silence the native complexes to allow your mutant complexes to be expressed for long enough that you can then isolate them. And that's what they did. And upon doing that, they have the ability to start mutating specific residues. And here in the FMO complex, there are exactly 2 cysteines. And one of the things that Bob noticed in about, I think it was 1993, was the fluorescence gets much, much brighter if you put in a reducing agent. And these, of course, are anaerobic bacteria. That's what they would be. The only exposure to oxygen is due to purification and handling. And so if you put in a reducing agent like dithionite, these things get much brighter. And if you get rid of these 2 cysteines, they stay bright all the time. You don't get that same oxidation effect. It does change things a little bit, but you don't get the same oxidation effect. And so we now finally had a tool where you can go in and you can actually, in a very detailed way, just by changing the redox state, change the FMO complex. And we know it has to do with quenching. So this paper tells you that the quenching happens precisely when oxygen is present because it takes these cysteines, these thiols, and changes them into thioradicals. That is to say, the energy transfer and the yield through FMO changes when there's an exposure to oxygen. And the reason this is in PNAS is this is a photoprotective mechanism. That poor little bug is energy starved and it's trying to grab every single photon. But boy, it doesn't want oxidative damage, so it has to rebuild a complex. So since it's got a 22-year doubling time, it can wait for the dust or the mud to settle after you step in its pond, and it can just turn off its photosynthesis for a couple hours and then get back to work doubling every 22 years. It's a minor thing. But if it were to burn out one of those complexes and have to have the metabolic investment to rebuild it, that really sets the poor thing back quite a bit, more than just a few photons. And it only takes a little bit of oxidation to ruin it. So this is a photoprotection mechanism that prevents oxidative damage when oxygen is present. And it comes from these 2 cysteine residues. And these cysteine residues turn out to be conserved across all of the Fenner-Matthews-Olsen complexes from different species. They're highly conserved. Then there was a paper on a different set of mutants from Blankenship and Scholes saying that the wave packets that are seen are robust to different mutations. Not the same mutants, that we're working with different mutants here, so people started doing spectroscopy on this. And then there's a paper out of our group where we use the cysteine mutants, and we find that many of these energy transfer pathways and rate constants change dramatically upon change in redox state. And we did this using both the double mutant in this paper and the wild type. And so we can tell that there are a lot of differences, both by perturbation of the cysteines and by change of redox state. And so this set us up to realize that all of these theory papers telling us how and why the energy transfer in FMO is or is not so efficient and whether this is relevant, we suddenly had a probe because now we can fundamentally change the energy transfer in these complexes. And boy, wouldn't it be neat if this were related to this sort of vibronic coupling in these coherences? And so this set up the study that I'm going to tell you about right now. And so when we look back at that Fenton-Matthews-Olsen complex, now here shown with all 8 chromophores, because we've realized there was an 8th chromophore around 2012 or so, and then we realized how we can handle it to make sure we don't lose it. This is also a Blankenship paper. So that's the one up at the top, but it's a little bit out of the way. Exciton 1 is in this chromophore in the lower left. I hope you guys can see my mouse cursor. Can you? Yes, okay. This chromophore down here is where Exciton 1 is. And here are the 2 cysteine mutants flanking Exciton 1. And down here in orange is a tyrosine tryptophan chain. Tyrosine tryptophan chains have been seen by Harry Gray in many redox active systems, and they're used to transport an electron out of the system. That tyrosine tryptophan chain had never really been spoken about before, but it is also highly, highly conserved in FMO complexes. So what Marco Elodi and coworkers did in that last paper, they looked at the different energy transfer rates, and they realized that even with these 2 cysteines gone, there was still redox activity in this complex, but you had to push it a little harder. You had to push it hard enough that you started changing these tryptophans and tyrosines. So that tells us exactly what we needed to know. The way that these cysteines cause quenching is they direct energy down here near this tyrosine tryptophan chain, and that's what can allow the quenching, the separating the electron, the hole, and then ultimately the refilling, the loss of thermal heat, rather than directing the energy towards the reaction center through Exciton 1. But the question then became, is this related to vibronic coupling? So we carefully went in and started looking at the excitons, and you can do this by diagonalizing the Hamiltonian. So Exciton 4, I hope you can see this. This one's quite bright, but you'll see some faded other chlorophylls in there. It's delocalized across these modes. And remember from Redfield theory, when you have multiple excitons on the same chromophore, a local excitation can cause energy transfer and relaxation. But of course, it's dissipative, and you'll need some place to put that extra energy. So a vibration is convenient. That gets to the Plenio hypothesis from before. Exciton 2 lives down here. It's also on these other 2 chromophores. This one you can imagine is going to be strongly perturbed by this cysteine right here. And then Exciton 1 is quite localized, and it's going to be perturbed by both of these cysteines. And so we go and we look at these different mutants. We can mutate 353 to an alanine. So one cysteine goes to an alanine. We can mutate the other cysteine to an alanine. And you can, of course, mutate both. And what you see here, ignore the slightly higher background. That's because we normalized the spectra, and one of them was a little bit lower concentration. The shapes change, but not a whole lot. You can see that there's a shift in this this exciton here that's over by 353. There's small changes in this lowest energy exciton, as you might expect, but they're very small. Some of them even offset. You see a larger change here when you have 49, but when you have both mutations, it tends to go away a little bit. There are a lot of very subtle changes, but one thing is clear: the overall spectral structure is roughly the same. These things have not completely shuffled. They've just tweaked themselves a little bit. There's some small motions that have energetic motions, small energetic changes that have occurred, but this isn't a different complex. It really looks roughly the same. And then what my students did, this work was led by Jake Higgins, along with Lawson Lloyd, Sarah Sohail, Marco Elodi, John Otto, Raphael Sayer from the Blankenship group, Ryan Wood, Sarah Massey, Po Che Ting, with help from Bob. And this published actually 2 days ago. I apologize for the slides still saying accepted, but it came out on Tuesday. So, you know, what we see here is when it's reduced, we see that a lot of the energy goes straight from exciton 4 down to exciton 1, and some of it moves through exciton 2. When it's oxidized, which means any small exposure to atmospheric air during purification, which happens, or during handling, which also happens when you're outside a glove box, you get a different energy transfer path. And we wanted to ask why. Why is that the case? Why is it that when you oxidize these 2 cysteines, and they're really air sensitive, that you get a different path? I mean, the protein sticks together, things don't move much, but the energetics change enough that these energy transfer paths change quite a bit. And I hope this foreshadows your question, JD, about what could be different in different labs when people are doing this. And it turns out we ran all our early experiments with ascorbate because we were using reaction center prep, which is, of course, a reducing agent.
Greg, sorry, Satish. Yeah. So if you go back to your previous slide, these excitons is, at around 850 nanometer has a, very nice vibronic structures, whereas the exciton at low energy do not have vibronic features.
So there are that's not a good interpretation of what you're seeing here. Mm-hmm. I understand why you say it. It makes a lot of sense. But there are actually 7 different electronic features here. And the Huang-Reese factors are very small. The reorganization energy is about 20 wave numbers. So these 20 to 35, people argue that quite a bit. And with such small reorganization energies, you're not seeing a lot of vibronic progression. What you're seeing is 1, 2, 3, 4, 5, 6, 7 excitons. Mm-hmm. This one is well resolved.
Yeah.
These ones are not. The lifetime in exciton 7 is fleetingly short, so it's very broad, and it sits on the shoulder of these others. And so it's not vibronic structure that you're seeing. You're really seeing electronic structure primarily. Mm-hmm. And I would refer to Rizzer Jankowiak's papers on the reorganization energy. He actually estimates it's closer to 15 wave numbers, and the people who are using 35 are wrong. And those are from hole burning experiments. The papers you mentioned from Miller typically use a much larger number to explain their data. So they're not quite consistent with some of those. Okay. But yeah, there's a lot of, the devil's in the details, and there's a lot of heated argument about this and what's right and why and under which conditions. Okay. These are fun things to talk about. Okay. But the message I want to give you for this is that these spectra are substantially similar, not identical by any stretch. You see changes, you see small changes, but they're substantially similar, enough that you could model what they look like, in fact. And here, what I want to show you is how we got some of this information. And so we look at our reduced and our oxidized spectra. We look at them for different mutants, and you can see that they are similar, but they do look kind of different. Like if you go to the double mutant, you can see that these features are much larger, and the intensities do change. The relative intensities do change here, and we want to go in and actually try and pull out these different rate constants. Now you get back to my Feynman diagram discussion, where I tell you all of these features are coming from multiple Feynman pathways. So you have to find ways to realize that like a diagonal feature up here can go away, or one up here can go away because of relaxation to, say, state 2 or to state 1. It can also go away due to a fluorescence or relaxation back to the ground state. The ground state bleach recovery can kick in. There are lots of different things that can happen. And what my student did is he used Hamanzani's dynamic Feynman pathways, something that they discuss in their book a little bit, but he had a clear insight, and he had to argue with me for about 6 or 8 months that this was the right way to think about it, because I kept telling him he was a little crazy. He wasn't. He was very smart. I was a little bit wrong. And so, very good student, very stubborn about this, and very right. And what you can do is you can use these dynamic pathways, and you could subtract. If you normalize, or if you have really good flat spectra, so you don't have to worry about normalizing, you can subtract them, and you can exactly cancel out certain physical processes, isolating each of these in turn. And the approach here then is that if you look at what happens when you have, say, a relaxation from one state to another, if you take a large enough area, you can get rid of that small reorganization energy. You can get rid of, now using some of Schall-Mukamel's formalism, some of the nuclear bath dynamics for either homogeneous or inhomogeneous processes. And then when you normalize them, the ground state bleach term is static. It will recover only when you have a dynamic pathway that causes something that started out in an excited state to end up in a ground state. And so you have a ground state bleach recovery that's a dynamic pathway. And you have stimulated emission, which is going to have some loss rate because that population won't last forever. And you can look at all these and you can start to figure out what these dynamic features are. You can get the ground state bleach and the loss as compared to the static ground state. And then you can look at a cross peak, and you have similar things there where you have both a bleach recovery and now also a stimulated emission feature that is itself dynamic. But this one comes from energy transfer between the two states, whereas this one is anything that exits state I. And if you're very careful, then you'll see that this has both an energy transfer feature and the loss feature. If you subtract the two of these, you can isolate just the energy transfer feature. And you have to go through this very, very carefully, making sure that you keep track of all of the different terms. But when you do that, you can go and you can get the different rate constants for each of these relaxations. And this is what my student did. And I just want to, don't worry about the table. I mean, I hate slides that are tables of lots of numbers. I mean, you never get much out of it. But I want to show you that there's something kind of weird going on here. Let's just take the 4-1 transfer time, for example. But you'll see this pattern in a few places. The wild type is about 500 femtoseconds. If you mutate 353, you break it. If you mutate 49, you don't do much. And if you mutate both, you break it. And that's what you would have predicted if I told you, look, 353 affects 4-1, 49 does not. Well, if you do both, you kind of know what to expect. You know, this makes a lot of sense. How about this one then? Well, let's look at what happens when it's oxidized. So the wild type goes pretty slow, and you can see it's actually a big change. The 4-1 transfer rate goes down by a factor of 3. So now it's 1.5 picoseconds. If you oxidize 353, it goes faster. Okay. You oxidize C49, it goes even faster. So what would you predict if you oxidize both of them? Actually goes about the same as wild type, a little slower, right? I mean, that now something's not additive in the way that you might expect. And there are a lot of these patterns. No change with 353, approximately no change with 49, significant change when you oxidize both of them. It's kind of unusual. And there's a lot of weirdness in these data. There are a lot of things like this where, you know, you can slow it down with one mutation, slow it down with the other mutation, but then slow it down less with both of them. I mean, there's a lot of weirdness in these data sets, and yet these are really quite reproducible. This is, I think it was 25 replicates where he extracted these and averaged them, and the error bars are really quite robust. So there's something kind of weird going on. And so you turn to modeling. You turn to try and understand what's going on based on the physical picture we have and our rates. And so what we realized was in Rizzer Jankowiak's model, where he had a nice spectral density, he really missed on the 4-1 energy transfer. And the only way you get that right is if you add into your spectral density a intramolecular vibration of the bacterial chlorophyll. So this gets back to that plenio idea that you're going to need some vibration. But one of the things that Jankowiak did in his models circa 2016 with Adam Kell, and this is really critically important, is he took into account the inhomogeneous broadening. So for example, in a reduced spectrum, which is what he was working with and what we're working with here, he allowed a certain amount of energetic disorder that's actually much larger than the width of a vibration. And so you average all of these in order to see your ensemble effects. And this is really crucial. And we can then use that same model and look at what happens to model the linear spectra and to look at what happens to our rates. And we found something fairly neat, that in each case, you can look at what happens with C49 or C53, and you can kind of predict what's going to happen to the various excitons based on which site they're near. So exciton 1 is on site 3, exciton 2 is largely on site 4, and exciton 4 is largely on site 7. So you don't expect much change to exciton 4, and that is to say site 7. And indeed, we don't have to invoke that. We really just look at what happens at site 3 and what happens at site 4. And so when we do this, we can say that, look, our Huang-Reese factor is roughly 1 when you're in the wild type, and this matches pretty well. We have a small change in the Huang-Reese factor then upon the mutation. But when we have a small change in the site energy when we oxidize, and that's because site 3 is close is close to these cysteines. But when we look at the energy transfer rates, we can actually map what happens. It's really nonlinear. These things, you see a red stripe through the middle of this graph, and when you oxidize it, you slow things down. When you do either mutant, you're going to find that you speed it up. And then when you do the double mutant, you come out on the other side. And all of these vectors are additive. That is to say, if you mutate C49 and then go to 353, it's just like going 353 and then C49. All of these changes here are additive in all the situations. And when we have the reduced system where we don't create that thiol moiety, we see much less change. That C49 doesn't have a whole lot of effect. And so this is fully self-consistent. And what's really happening is the site energy for site 3, which is this exciton 1, shifts away. The gap between 4 and 1 shifts away from this vibration. And once you detune that energy gap from the vibration, you can recover all of these different dynamics. And so what's happening here is when exposed to oxygen and you oxidize C49 and C53, you effectively shift that energy gap off of the vibration. And then when you mutate those away, you start to bring it back, depending on how close the residue is to the particular site that you're affecting. And so you can see in these situations that the C49 change gets you back towards the wild type reduced, and that's because of the close proximity there. The C53 mutant does matter, but typically not as much. It changes a little bit in the binding and the motion around it, but not as much of a change in the site energy. So all of this is fully consistent. And what it tells us is that nature is actually exploiting this in order to change the environment around these particular chromophores, site 3 and to some degree site 4, but mostly site 3. And when you detune that, you direct the energy not from exciton 4 to exciton 1, but you bypass it through this exciton 2, which is near the tyrosine tryptophan chain, which allows you to have quenching. And you can go through your red field theory, just copying Jankowiak's model and looking at these. And again, here everything's additive or multiplicative for the spectral densities, Poiseuille's factors, excuse me, the spectral density coupling change. So if 353 affects it by -60, then you're going to expect C49 to be 0. Both of them are -60. Everything is self-consistent. The oxidation we had to solve for, and then 353 is going to cause 0 change. -20 for C49. Both of them is -20. And so here's -60, -100, and -160 is -40. All of these add up. Everything, so vector calculus is respected in this table. And then you look at the red field and the experiment, and they're not numerically exact. It's an approximate model, but you see these trends where you make a mutation, and in theory it gets slower. You make another mutation, no change. You make them both, and you're back to the same place, just like the pattern you saw here. But then you get down into these where you make a mutation, it gets faster. You make another mutation, it gets faster. You make both mutations, it's back to where you started. You see those same kinds of non-monotonic trends. Now, it's not exactly the right number, but our model is approximate, but it captures exactly what's going on. So I don't know if these numbers should really be 0.8 or 0.79. We don't have that kind of resolution. But the patterns survive.
Greg, can I ask a question? Just to get a feel for this. The cysteine oxidation, what does it lead to? Does it make a disulfide linkage?
It makes it into a thiol moiety.
Sorry, the disulfide becomes a thiol. Sorry. So disulfide.
The two don't link. There are only two cysteines in the complex, and they're not close enough to create a disulfide.
Okay, so how do you think about the oxidation? What is the chemical nature of cysteine under oxidizing condition?
You are seeing a thiol radical. You're seeing a thiol-free radical, and Blankenship has started to look for this with ESR and sees evidence of it. So you do have a radical on the sulfur.
Is it possible that, so if you were to do a simple, it's hard to interpret pump probe in these things, but is there a possibility of capturing that thiol radicals in your can these energy transfer, what my point here is, can these energy transfer pathways actually sort of look for ways to mitigate the radical rather than?
So we have seen no evidence that, at least on the timescales that we've looked for, we see no evidence that the electron or hole from the optical excitation is interacting or reacting, maybe I would be a better way, with the thiol radical, which is I think what you're getting to. Is there an ability for this to then say oxidize a chlorophyll or something? And we don't see any of that. So that is to say there's no permanent damage or photochemistry from these radicals. Instead, it just appears that it tickles the complex a little bit. So everything's reversible. That once you create these thiol radicals and you shine light on them, if you then reduce it again, they're fully functional. They survive it. They are not damaged. And I think that's actually evolved functionality precisely to make sure that you avoid photochemical damage in the presence of oxygen. So this is a way that the oxygen changes the electrostatic environment just a little bit. They're somewhat distal in order to shift the energy transfer to the tyrosine tryptophan chain, which we do believe is actually interacting with the quenching on these long time scales. Now we're talking nanosecond time.
Yeah, I'm just wondering because you know the Azurin systems, like you've done some work at this also. Any cysteine radical, and if you have a tryptophan or a tyrosine nearby, there should be some quenching pathways for the cysteine, which would stabilize through the tryptophan radical, because there are proton coupled electron transfer pathways that can stabilize an O dot as compared to S dot. So I was just wondering if there is an intrinsic way to move that hole across through, while you're submitting this much of energy into the system, or the question would be, are you exciting every population where there is an S dot, or you have a mixture of SH and S dot?
So when we do this chemically, it's our understanding that we certainly go to entirely SH when we have a reducing agent.
Okay.
There's no question with
no question about that. Yeah.
That definitely. Now, when we have the atmospheric oxygen, we're not working hard, we're not stirring it up,
right.
But it's our understanding from Bob's experiments and the sensitivity we see in the fluorescence lifetime that we are rapidly and rather completely oxidizing these cysteine radicals.
Okay.
The one up here is too far away from this tyrosine tryptophan chain to ever have the kind of exchange that you're talking about.
Okay.
There are some other tryptophans that are bound to the magnesium in the center of the bacterial chlorophylls. Those are chemically inert.
Okay.
Those are not going to have that same kind of reactivity.
Okay.
Now this one here is not close, but not terribly far. And one could imagine some sort of either through bond or really long distance outer sphere Marcus type transfer process. And I don't know enough to know if that's the case.
Okay.
That's something it would be interesting to get. The ESR measurements that Bob was looking at strongly suggest that these thiol radicals are extremely stable.
Okay. Thank you.
So I think given that, I'm guessing that there's not a coupling there that's significant.
No issues. No issues. Thanks. Yeah.
I had a quick question about the modeling table that you had shown, Greg.
I'm having trouble understanding you, Vivek.
Could you say that again? Mic. Yeah. Could you put your mic close to the?
Yeah.
So, can you hear me now?
Yeah, better.
Yeah, that's better.
Actually, I had a quick question about the modeling part of things in the table that you had shown. So, is that taking into account the entire spectral density of bacterial chlorophylls? And if so, I'm thinking about, let's say you change the site energy and you move away from a vibrational frequency, but we know that the vibrational spectrum is quite dense in the low frequency region. So is there a chance of, actually moving away from a particular frequency, but then getting into a resonance with another vibration?
Yeah, so the spectral density that we took here does not allow that, but of course it's oversimplified, which is I think what you're saying. So when Rizard and Adam Kell modeled this, they just used the simple ohmic spectral density, and they really nailed all of the rate constants except the 4-1, which they had as picoseconds, when in reality it's about 500 femtoseconds. And so what we did, knowing that, was add a bump to the spectral density here, just to see if this is consistent with this kind of vibronic coupling. Now, you're absolutely right that there are other modes that can couple to this. And indeed, this particular one that we have added is a very strong mode, as you're well aware, but it's not one of the ones that we see most strongly in our spectra. Very, very well agreeing with a certain PNAS paper from long ago. And this mode is the one that we've added. We probably could think about how other modes couple, and we could refine the spectral density using something from, say, David Coker or Kleine-Katoffer, and think about that. We also should think from last time about the motions out of that Frank-Condon region, and we have to, I think about non-equilibrium effects too. But here in a Redfield model, you don't get that. You get a thermal bath. It's a reservoir. So there is no explicit vibronic coupling where we take a vibration into the system. That, I think, and I've been talking to Tomas Manchal about this, is probably a more sophisticated way to model this, to actually take those specific vibrations, not merely as harmonic modes of the bath, but actually bring them into the system and allow a splitting of an exciton into effectively a vibron and a lower energy exciton. And there'd be a sort of a parametric downconversion process there. But this is, right now, we just have a kind of simplified model to see if this is enough to explain the data. And I think while there's definitely something missing here because we don't have coherent coupling to the bath, there is also something here that explains what's going on, that when the gap moves on and off the particular vibration, it's important. I've ignored things like the vector coupling and the transition dipole of a particular mode relative to the change in transition dipole as you move between these two excited states. There are a lot of subtleties here that are not part of this model. So it's an oversimplified model that recovers the nonlinearities that we see largely across the board, where we do recover many of these, and you can kind of see some of these patterns where in data, and in particular the non-monotonic patterns, the things that are not additive, are recovered out of this model. So I think it's a first step. I don't think it's the last word in accurate modeling of these, but there are definitely many vibrations in both the protein, of course, and also the chromophores. There are a lot of atoms in a complex like this.
Okay, thanks.
Jayashree?
Yeah, hi, Greg. So, so just a couple of questions directly related to this table. So one thought is, is it possible that the mutations are changing your couplings as well? Because right now you have the site energies.
Yes, absolutely. And they must be making those changes.
It makes sense.
There have to be, but those, if we look at what comes into those, it is a little more subtle. So this is a minimal model, and it's sufficient to reproduce what we've got. We have not been able to calculate accurately what we think it would do for those other off-diagonal elements of the Hamiltonian. Right. On the other hand, if I look at how we typically calculate those off-diagonal elements of the Hamiltonian, the site basis, there's an orientation component in the dipole-dipole coupling. There is a distance component to the dipole-dipole coupling. And then, of course, there is this electrodynamic factor that's going to come in as a dielectric constant of sorts, maybe a distance-dependent dielectric constant because of the nature of the system. And of those, we can be pretty sure the geometry is not changing. Crystal structures are coming of this, and they really confirm that we do not have changes in the geometry of the system. So it's an electrostatic or electrodynamic change. So in terms of the off-diagonal elements, we would expect it would have to come into that dielectric through electrostatic fluctuations at the optical regime. But this is a fairly static coupling. So the optical frequency dielectric constant, it seems like it's going to be pretty stable. So we think most of the action will be in the site energies. And what our model shows is that putting it into the site energies is sufficient to largely reproduce the trends in the data. But there have to be some changes. They may be subtle, they may be large. I expect they'll be subtle.
So sort of a quick related question is, so how are these site energies sort of parameterized by Manchal? I guess Manchal is doing this theoretical work, or?
So I'm trying to get Manchal to do this theoretical work.
Oh,
I think that would be
okay, so this is not
from saying that Manchal is doing this theoretical work. Because, I mean, Tomasz and I are good friends. We've known each other since we were postdocs together. Neither one of us does what the other one says most of the time. So, which is great. I mean, we both are creative. This is fine. But I'm trying to twist his arm. If you want to do it, I'm game. You know, we should all be honest of who's working on what, and we can talk as a group. But absolutely, I think there's room for this to be done. I'm trying to get people to think about this more deeply. We will not be doing that ourselves, but we're happy to consult.
Yeah, because I was just wondering if there's some sort of ab initio component in this parameterization, or it's sort of you know, sort of trend-based, or sort of experimentally motivated.
Everything you see here is experimentally motivated. This is not calculated. This is us coming in saying, look, let's start from a baseline from a reduced system. Let's look at, you know, how close these residues are and make sure we don't make changes that are outrageous, where it's going to affect, you know, a distal residue, a distal site more than, you know, a neighboring site based on the distance in the three-dimensional structure. Let's make sure that the changes we make are additive, such that we're not just pulling numbers, so there's at least some self-consistency to our model. But we are doing this entirely to see if we could find a set of parameters that explains this data. And we have tried it without making changes to the Wang-Rees factors, and we simply can't express it without allowing, especially with the 353 mutation, which doesn't affect site energy as much, but seems to affect some of the motion or some of the dielectric, is somehow that coupling to this bath seems to change, and it couples a little differently.
Yeah, I think it'd be nice to get the relative energies from first principles or something that could be.
I agree.
To mutation. So anyway, just yeah, thanks a lot.
I agree completely. And you know, Ulrich Kleinekatoffer and David Coker have worked hard on this for the native wild type for a very long time.
Sure.
And that's just, it's a tall order. Alana Spuru also did some work with QMMM calculations on that. It's a very tall order to get this right and be consistent.
Yeah.
And you know, before you tackle this table, I would tackle that first paper by Kell and Jankowiak and just try and get the basic wild type complex, and make sure you agree with what has now been decades of refining of that Hamiltonian and spectral density to start. And then we can start thinking about the mutations once we get that part right. But it's hard. It turns out to be quite a hard calculation. A lot of people have rushed into this thinking it'll be pretty straightforward.
No,
And it's eaten a lot of time.
Yeah, it's going to be difficult. Okay, thank you.
Yeah, it turns out to be more, even to the experts, and I am not expert on this, it has turned out to be much harder than you might have expected, or that they might have expected. So I provide warning, but that also means that that's an opportunity for insight, right? I mean, that shouldn't be the kind of statement that dissuades you from doing it. That should be the kind of statement that, you know, forces you to think carefully because other people have tried, but you know, you're just always one insight away from being able to crack the whole thing open. And boy, will people be impressed, because a lot of people have tried. So you know, don't let that dissuade you. It's not my goal to say don't do it. It's my goal to say pause and think carefully. But by all means, if you can solve it, people are going to love it. They're going to want that. There is need in the field for exactly that.
Thank you.
Ravi Kishore, you have a question?
Hi, Greg.
Hello.
So just you just mentioned that there is no geometry change. Yeah?
There is. I didn't hear. Could you say again?
No, just in reply to what Jesha has asked, you're saying that there's no geometry change on this mutation.
The geometry change for these mutations are extremely minimal.
So with the packing and all, nothing is not getting affected.
That's right. That's right. When you lose that proton, it does not provide a whole lot of spatial rearrangement.
So, but
the thiol and the thiol are roughly the same size.
So thermal fluctuations, but the dynamic changes are there, but they probably could get affected. And site energies, of course, are getting affected.
Site energies, of course, are getting affected. That's the electrostatics are going to be the major change. But yes, we think that so the major change will be site energies because the electrostatic effects. The next thing that we think is going to change is that the spectral density, the coupling to the spectral density, that Wang-Rees factor that we're talking about. And that comes largely from the fact that you're interacting with things with slightly different charge. So as soon as you change a nearby charge, you're going to change the ability for that vibration to couple and relax. because it also has a transition dipole moment.
Yeah.
The geometry, I think, is going to be a far less important contribution.
And what about this? So the mutations you're saying so does it during any of these mutations, do you go from a strong coupling regime to a weak coupling regime, or vice
No,
versa?
we don't see any changes that are that substantial. And you know, if you look at these rate constants and you look at the spectrum, if we went from strong to weak coupling, we would really expect to see wholesale changes in the spectrum. And we have played with other systems that tend to do that, where we can put dyes on DNA constructs and control the mixing and see large scale changes in the vibronic coupling and calculate all of those. None of that apparatus is relevant to this problem here.
And what about the
These
modes?
are very minor perturbations.
Yeah, okay. And what about the modes? Because the modes also probably will change because of these mutations.
The modes in the bacterial chlorophylls it's not as clear to me that when we're talking about you know, a ring mode of this bacterial chlorophyll chromophore, it's not as clear to me that that ring motion is going to change necessarily because of these thiols. I think diagonalizing the modes of the bacterial chlorophyll based on the change of a thiol to a thiol radical, I don't anticipate wholesale changes at all. I mean, if I were guessing, I'd say like third decimal place kind of things. Like, will they change numerically? Probably, but will it matter? Absolutely not. You know, is it 267 or is it 267.5? But compared to, let me go back to the slide. I'm going the wrong way. I apologize for the flashing of the slides. If I compare it to the static disorder that we see just from the protein, if I move this vibration a couple of wave numbers one way or the other, it's not going to affect any of these dynamics.
Okay. Yeah.
It's the larger motion of the site energy that actually is going to affect the dynamics.
Okay.
So yes, you'll retune it. It might, instead of being a 267 wave number mode, it might be 269, but compared to the energetic disorder in the protein complex, that's not going to make any difference in the ultimate dynamics of the ensemble.
Thank you.
Okay, Greg, we'll let you finish the talk and then we'll have more questions.
Sorry. I appreciate the questions. I mean, this is actually the fun part of coming somewhere to give a talk.
Let's finish.
And indeed, I am basically going to wrap up that when you look at this complex, you know, in contrast to the picture I gave you yesterday, where I was just looking at the chlorophylls, it suddenly becomes clear that there is evolved and indeed conserved elements of the protein structure around this that change the functionality of the electronic structure. So from the point of view of a spectroscopist who, up until this experiment, was basically just looking at the green chromophores, now suddenly we can begin thinking, as many of you are asking, what these cysteines do, what the tyrosine and tryptophan chain does, how it operates, what's that chemistry, what's the microscopic mechanism of the quenching, how do you redirect the energy instead of going here, down here to go around that bypass near that tyrosine tryptophan chain, which is what we see, and how does that affect the overall dynamics? And then there are questions that someone like Alexander Alea Castro would really like to ask of when you have two pathways from, say, site 4 down either via site 2 or to site 1, if indeed they're coherent energy transfer pathways, and we have reason to believe they are from some of our other data, then suddenly you can get interference between two pathways. You can start to think about elements of, say, quantum kinetics, where two pathways can interfere constructively or destructively, and there can be something kind of interesting. And this was the noise-assisted quantum transport process coming back again. And it was precisely the one that Plenio mentioned in 2009 with different phase across two different legs of an interferometer. So some of these patterns are really suggestive that there's something cool. It's not what you might think where you go 100, 0 or 0, 100. It's actually 50, 50 or run it all down that other side chain. So there could be something very interesting here for people who start to think about the quantum dynamics of this. And with that, you know, it's clear what we have to do is go back to the lab. We have to look at the coherences. We have to look to see, are those oscillations that we see affected? I'll give you the preview. The answer is yes. And indeed, this may be why others who haven't been putting in reducing agents see different things and have different timescales. It may not. This will evolve with time. And I note that the particular student that I picked here, Ved Singh, came from IIT Bombay. So I wanted to throw that in here as well. And with that, I want to thank the same people that I thanked yesterday for all the same reasons, that this work is done by the students in the lab. It's not done by me, though I do like to consult a bit, perhaps more than they want sometimes. Much credit to Jake Higgins on this particular paper because he stuck to his guns and argued with me on the analysis strategy that broke this problem open because I didn't think that was the right way to think about it. He taught me quite a bit. And now I think we have a very nice paper that just came out this week that we're proud of. And I thank the rest of my group and of course, Bob Blankenship and Raphael for the sample and the consultation on the biology funding. And thank you guys for your attention with the talk. And I'm happy to take more questions. I can be here as long as people want to ask various questions. And again, if you weren't here yesterday and you do come through Chicago, please come visit us. We're just south of the city. That's a few miles south of the main part of the city. Right in the middle of campus. You know, the med school's over here, math and science and physics are here, and we're sitting right there under this quad. So come see us, we're underground. Doors are always open, except during COVID when they're locked closed by my university. But soon they will be open by the time you can fly and visit us. So please do that if you're coming through. We get a lot of drop-in visitors in winter when a snowstorm happens and you're stuck at O'Hare. So if you find yourself stuck in Chicago, we'll give you a desk and an internet connection and a tour of the lab. Please come visit us.
That's awesome. Thank you, Greg. Wonderful. I would like all of you to please join me in unmuting your video, audio, and please thank Greg once for a big round of applause.
Thank you.
Thank you, Greg.
Thank you. It was my pleasure.
Yeah. So the floor is open for more questions. So please ask your questions heart out because he's excited. He's still late in the night, but he will answer the questions.
Yes. So I think Jayashree raised the hand. Just Jayashree, go ahead.
Yeah, okay. Here I go again. Okay, so I have a question about the enact mechanism. So I guess that went through a little bit quickly in your talk, but what I'm trying to understand is, so is it possible that you're able to control the bath in some way so that you can assist the energy transfer through the bath system dynamics? So can you sort of briefly comment on that?
We are not able to run that experiment, but what you describe is precisely the experiment that was run on the 10-qubit quantum computer, where they can just introduce noise and dephasing from external perturbation. So they take a very clean ion trap and they make a dirtier ion trap, and they can actually watch the transport change. The particular ENAQT model is basically a bastardization of a high temperature limit. And so there are some issues with how dephasing and temperature are taken into account there, and dephasing is used as a proxy for temperature, even though the entire model is in the high temperature limit as you move to lower temperatures. This is something that we tackled in my group with some Keldysh-Green's function formalism to actually incorporate the quantum transport as Paul Brummer would have counseled in the infinite time limit, the frequency domain limit, and can show as we use an incoherent source and an incoherent trap, that the dephasing in the retarded Green's function is precisely what determines the branching factors, and you recover all of the ENAQT dynamics that were predicted by their high temperature model correctly. So I mean, it gets the gist of it right.
I guess the sort of idea is that your bath is still very big, right? So it is still very big that it doesn't affect your overall landscape of the system bath. But at the same time, what you're doing is to sort of controlling some local sort of properties of the bath so that you can tune the sort of energy transfer rate, so to speak, right?
Yes, that's right. You're effectively tuning the dephasing of the system.
Right. Okay.
And that's the heart of that model. And there is a little bit of non-physicality in the way that was originally built, but it captures all the right physics. And so, yes, you're allowing certain electrostatic fluctuations to create enough of a change in the energies on a relevant timescale such that the things that were in phase suddenly come out of phase, and you start to see that dephasing across the ensemble.
I see. Yeah, interesting. Okay, thank you.
Questions from students, I would like.
Yes, that would be good.
Ask your questions if you do not understand the spectroscopy, or this is an expert. We hardly get to hear from him, and this is the opportunity.
I think before they just prepare themselves, I have a sort of a very basic question. So these multi-excitonic system, when you considering, they are in different environment. These excitons, when you named it 1, 2, 3, 4, 5. So the dielectric environment of these Frankel excitons would be very different. So how does affect the rate of energy transfer? Because the binding energy of these excitons, the way I'm thinking about this problem is the binding energy of these excitons would be very different in different environment.
Yeah, so, I think the binding energy is probably not the right metric for this type of exciton. I mean, this is a tightly bound exciton no matter how you cut it. You're not separating the electron from the hole, no matter what you do in this system. But you're correct that the electrostatic environment varies throughout the protein. We actually see that in the distribution of site energies, and it's rather significant. It's one of the reasons, well, it's one of two reasons. The other is that the fact that there's 7 of these that couple. We were absolutely shocked by the data I showed you last time, where these things tend to move in tandem. That I would expect, because of the different environments as you cite, and the symmetries or lack thereof in an asymmetric complex, they're in a 7x7 Hamiltonian, would almost make that impossible. And yet that's what the data shows us. So that is something that I find very, very curious, because I was one of the early proponents of this model that things are moving in sync. But I remember very clearly what I said to my postdoc is, this has to be wrong at some level. Let's go show that it's wrong before someone else shows that we're wrong. And he came back with some really interesting data that suggests that maybe we weren't quite so wrong. Of course, that's gratifying in one sense, but I still don't fully understand it, and I find it surprising. And I find it surprising for 2 reasons. One, that you cite these site energies differ, and when they differ, all these excitons should be in different environments, and it's reasonably significant. And then the other is just the symmetries, or actually lack of symmetry, in that Hamiltonian, such that you get lots of these different pairwise excitons, some that are quite isolated, and yet still the motion of the Franck-Condon region seems to be extremely uniform. Now, I do think someone can tell me that, look, this is bacterial chlorophyll, it's a pi to pi star transition, no matter how you cut it. They're all going to do exactly the same thing. And if all members of the Hamiltonian do the same thing, it's a fully symmetric mode. And maybe this is exactly what you'd predict. But it still isn't exactly what I would have predicted. And I maintain that just because of the geometries and the structure. But the data is the data. I mean, this is what we see.
Okay.
And so I'm struck trying to explain what we see, even though I wouldn't really have predicted that this is the way it had to work. I mean, we kind of got that phenomenologically as an easy model to explain what's going on, but it did not gel with my microscopic intuition as a chemist. And it still doesn't, but now we have better information to suggest that that idea probably really is right, which means that there's an opportunity for insight there.
Okay, cool. Thank you.
Yeah, I had a question. Can I go, Jerry?
Yes, Ravi. Yes.
Yeah, so Greg, I wanted to actually talk about the diversity of spectroscopic techniques that are used generally in the field, right? Even if you go to 3rd order, right, as you pointed out right in the beginning, you have photon echo, you have different, you have transient grating, for example, as well as you have pump probe spectroscopies, but, some are more popular than the others. So I was wondering, if you could comment on the, application of, a diverse range of these, N-wave mixing techniques, basically, to probe, for example, your FMO complex, for example. So can you comment on that?
Yes. So Min Cho published a very nice paper. This was back in the late 90s. I think it was 99, showing that the frequency resolved photon echo, that is to say the 2D photon echo experiment that I've been telling you about here, contains the entire 3rd order nonlinear response. That is to say, if I take the imaginary part, I can get a transient grating. If I integrate on the excitation axis, I can get a pump probe spectrum. This is the complete 3rd order nonlinear response. So this technique is, in some sense, contains all the information. Now, your question about which ones are more popular and why, this also depends if you know what you're looking for. So when I do this and I get, say, 100 by 100 pixels in my spectrum, I could have designed a pump probe spectrum experiment with an nice lock-in amplifier to look at one particular pixel with one color of a pump and one color of a probe. And I could spend all of my acquisition time resolving that one pixel. And I would have much, much better signal to noise. So on one hand, the 2D spectrum shows you everything. On the other hand, it's the wrong way to measure anything. Because you could always design a better experiment to look at a particular effect or a particular pixel. What I like about the 2D experiments is they're a platform for discovery. When you go in and you don't quite know what you're going to see, they provide you with context. They provide you with a view of the entire system so that you don't just tell one story about one state and not know if you're on the edge of a peak or in the middle of a peak, or you've integrated something, or if you see a beating between two pieces. All of that shows up. So I view 2D spectroscopy as a wonderful platform for discovery where you think there's something interesting, but you don't know what's going on. If you have an idea of exactly what you want to measure, we can always build a better and more sensitive third order measurement that gets that particular piece of the spectrum. And so a lot of this discussion of how do we handle this within the third order comes down to that. Now, you also mentioned n order mixing, and of course there's fifth and seventh and on up. But unlike my NMR colleagues where they have pi pulses, I have something on the order of pi over 10,000 pulses. So as I go to higher orders, it becomes much more challenging to get the signal. Now, if it's resonant, we can do this. And in my group, we've done fifth order electronic. One of my former postdocs, now professor at Michigan State, Elad Harel, has done simultaneous third, fifth, and seventh order to look at mixed vibrational and electronic effects. It's a beautiful, beautiful experiment. I believe his acronym was Pro Gamers. He comes out of an NMR background, so he's better with acronyms than I am. And in fact, he made up all my good acronyms. And so, you can do this, but they become very hard. And then pointing back to my theory colleagues and Shaul and his group, it becomes really hard to nail down all of the fifth order pathways in order to simulate the right spectra. So when we did a fifth order electronic experiment, resonant electronic experiment on Nile blue, we see some interesting vibronic features that we have been unable to model and simulate properly. And I honestly stopped with the higher order experiments as soon as I got to fifth order and I couldn't properly simulate Nile blue. This is Nile blue in solution. This is not a protein. This is not a multi-chromophoric system. I just couldn't handle where the cross peaks were coming from the vibronic progression accurately enough to know what I was looking at on my control experiment. And then we didn't go further because I didn't know how to interpret those spectra when I got them. That I'm seeing cross peaks that I didn't expect. And I'm sure it's my shortcoming. I mean, I'm sure there's not a problem with the theory. There's a problem with my ability to create the right simulation based on the right parameters that have to go into it. I mean, it's all in Shaul's book. There's no doubt about that. But it becomes really hard to build it right. And so for the higher order theory, unless you have a simplifying notion, Mark Berg with seventh order Raman echoes has done that. Mark Berg also with his Muppets experiments has done that. Elad Harel with his coupling, because he gets third, fifth, and seventh at the same time, can actually cross-reference them. And he has been able to provide some of that context for those measurements. But the nth order measurements in general are extremely hard. The nth order measurements, when you use symmetries, as Berg does in the time domain to compare multiple population times, then you have an ordering principle that makes it very easy to interpret. So homogeneity rate constants in the case of Muppets. But there has not been a good enough general theory that we can understand based on the complexity of the molecules. It's not a light matter interaction problem. It's a molecular problem that we can go to those other nth order spectroscopies reliably.
Okay.
At least in my opinion. I mean, Elad might disagree and say that he does understand it, but he is smarter than I am. So that may be all the explanation I can give in that particular instance.
Greg, I mean, I think in philosophy, this is what I was trying to understand. I'm a theorist, so overall, I can understand essentially the diagrams and essentially how to get the responses right. But then the question is it really useful to experiments to look at all these different perspectives? So I think, I appreciate the point. in terms of the implementation as well as interpreting the signals. I just think that they give multiple perspectives of the same problem. And sometimes it may be useful to resolve the controversies, for example. And I was wondering if this was
absolutely. Some of my best, some of our best experimental ideas have come from interaction with theorists doing exactly this and going back and forth to present what a theorist might think we should measure, and in other cases what we think we can measure, and sometimes there's a middle ground. I mean, I remember getting a call from Shaw once on a quantum transport problem where he said he thinks that we should be able to have this in our signal, and I called him back about an hour later saying, good news, we have it in our signal. Bad news, your model doesn't conserve energy. He hung up on me. He called me back about 2 hours later and he agreed it didn't conserve energy, but he fixed it because that's, Shaw's just that good. And then we were able to publish a nice paper together. And I think this marriage of theory and experiment is critically important. I do have some theory-oriented students in my lab who work with this, but we're always open to collaboration. We're always open to suggestions of ideas and experiments and ways that we can exploit the symmetries in either the light matter interactions or the molecular systems in order to pare down the information in the spectra and actually get at the piece that resolves the controversy in an unambiguous fashion. Because often with these spectra, you see a lot of different blobs and there are different ways to interpret it. And it can be quite subtle. And you might think you have it right, and then someone comes along and looks at it a little differently. Oh, you haven't ruled out this, and it's often true. And then you have to define a new experiment to get at that. And that's both the fun and the challenge. Okay. But yes, I think theory and experiment working hand in hand in this space is utterly crucial.
Okay, cool. Gursaheb, a student question. Gursaheb, then I have 2 questions and then we'll conclude.
So I want to ask about that Feynman diagram you were talking about. So how, when the third ray comes, why the complementary one goes to the ground state? I didn't understand that. When you were talking about the excited and ground state picture.
Yes. So you in any of these Feynman diagrams, you have to end after your signal comes out in a population. And this comes from the fact that observables in the density matrix formalism are taken with a trace, the diagonal elements, which are the populations. Now, it doesn't have to be a ground state population. You could have a situation where you end in an excited state population. But in that particular instance, where in my phase match direction, I'm getting my signal out, I knew that the last interaction had to be on the left. And therefore, which I guess my video is mirrored, I apologize, that's just not working at all. But I knew the side where the last interaction had to happen. It was opposite from the side where the third interaction happened. So once that third interaction put me into a ground state, I knew that my signal had to move from an excited to a ground state. I could have, instead of putting that third pulse as an emitted photon, if you want to think of it that way, as an absorbed one. And the photon picture is a little tough in a field-based expansion, but it's conversationally convenient. If I put that energy in, then I would have had to end up in a doubly excited state, an F state with the population, and I would have seen a different effect. I would have seen an absorptive term, and that would have changed the diagram a bit. And so you have to consider all the possible diagrams. The particular one that I drew, because I needed to be in the minus K1 plus K2 plus K3 phase match direction, I knew that last signal had to be emitted on a particular side. And indeed, it's redundant if I do it on both sides. So Shaw tells us that you take that out in that direction. And when you do that, you have to end up in a population, and that really ties your hands as you work through the diagrams.
Okay. I have, okay, there is a question by Saurav Saraf. Saurav, unmute yourself.
Hello, Greg.
Yes, hello.
You mentioned that in the phase matching direction, we get zero background. So what is that actually? Like, can you elaborate on that?
Yeah, so this is something that's interesting, and the first time you see it, kind of surprising, that you put in a laser pulse from one direction, a laser pulse from another direction, a third laser pulse from another one, and you get out your signal in a direction that is not any of those three that you put the laser pulse in. And when that happens, what I mean to say is you're not looking for a small perturbation on top of a whoppingly large laser pulse. So, imagine an absorption experiment with a laser. If I want you to see how much light is absorbed, you have to put your eye on the other side of that sample and stare at the laser. Not a good experimental idea. Don't do that. But you're looking for small differences where you might absorb 1% or 1 part per million. And it's very hard to measure 1 part per million. Compare that to, say, a fluorescence microscope, where the photon is fluoresced in a unique direction, and it's dark except for that fluoresced photon. And that's what I mean by zero background. The other laser pulses don't come out in the same direction. So you are looking at something where you're either seeing signal or you're seeing nothing else. It'll be dark or you see signal. You will not see one of these whoppingly large ultra-fast laser pulses coming in and burning a hole in your detector.
Okay, another question, like you mentioned that quantum transport and algorithm by Asbury and Guzik. So can you elaborate something on that?
Yeah, so there's a sort of a long history with that, but when I first gave that talk, Alon erupted and was upset that I would say that this was a quantum algorithm or quantum mechanism, and then a couple months later he calls us. It is. I've proved it, and I can show you which one it is. And he had submitted the paper. Meanwhile, Martin Plenio had done something substantially similar, though the formalism's a little different, roughly at the same time. And those are the 2 papers that I cited. They were the first 2 papers, which is why I cited them. There have been many refinements from those papers. I cite them because they were the critical insight in my mind that set people off in this direction thinking about it. Both of those initial papers are brilliant, but somewhat crude. I cite them because I think they have the right ideas, and they were the introduction of the ideas to the field. I think if you talk to Plenio and Alon, they'll tell you to read different papers after that to really get to the heart of the issue. So those models were a little crude, but I think they were brilliant. Actually, I point you to Alexandra Alea Castro's paper for much more sophisticated and probably much more correct models that build on these ideas. She was not first through the door, but she is arguably best.
So another very basic question, why do you only look at coherences in spectroscopy?
Yeah, so anytime we look at something in spectroscopy, what we see is an electrodynamic fluctuation. And that is generated by a coherence. So we can't see a static E field. We see an electromagnetic wave. And we see a photon, if you want to think of it that way, but forgive me for being classical. We see an electromagnetic wave. The electromagnetic wave comes from the fact that you have different charges that are oscillating. And in quantum mechanics, you get that oscillating charge only when you have that superposition character in a wave function or this coherence character in an ensemble.
Thanks a lot.
Yeah, so you can never see an excited state. You just see the coherence.
Right.
If anyone tells you otherwise, don't believe them.
Thank you, Saurav, for your questions. And I would like to ask 2 questions, Greg. The first one is with respect to when you're looking for these, looking at these very sensitive FMO complexes. Do you look at the damage caused after the experiment? Because these must be taking quite a bit of time to sort of collect data at room temperature, for example.
Yeah, so we do pay very careful attention to that. And they are certainly more robust at low temperatures. So when we repeat this experiment, we can move the cryostat to a different point. We can sample in random order. We can check that if we run the experiment and we run the experiment on the same point, we don't see significant degradation or loss of signal. And we do run all of those. We run these at much lower powers than we used to. So Tobias Brixner in that 2004 paper was running at like 10 nanojoules per pulse over a 70 micron spot size. Okay. When I published in 2007, we were down to about 1 nanojoule-ish per pulse on the same spot size. When we published in 2010, we were down to hundreds of picojoules in that same, and yet our signal to noise is growing for all of these. Right. And so as we engineer better spectrometers, we lower that, and that gets us out of this damage threshold region. So Tobias was quite careful, but we worried about it because you get multi-exciton effects. You worry about 5th order contributions. You have to very carefully check that your signal is of the proper order with these power dependencies. Right. And so we try to go to the lowest power we possibly can. But again, this is a compromise like everything else in the lab. You get much better signal to noise if you hit it harder, but you run the risk of damage.
Right. So since I come from a PS2 background, photosystem 2 background, so we always had a functional assay for working of PS2. So we are doing some experiments, optical experiments on it, and we know if there is a damage, we can go back and run the oxygen evolution reaction. For FMO, is there something that you could do independently to check the integrity or the functional integrity of that?
You know, you have the linear absorption spectrum and you have the fluorescence yield, which we've already talked about as a function of redox state. And that's really about all you have.
Okay.
You know, I mean, you could do crystallography, I guess, as well.
Yeah.
And, you know, even in some of the hole burning experiments where people have looked at this, it's a really robust complex compared to something like PS2.
Okay. Yeah, so no, I just wanted to know, this is some practical consideration. The other part of the question I had was the data analysis. So for all 2D spectroscopies, one of the things that appears to me, because I'm not a practicing one and I intend to think about it later, but the big thing is how to analyze data, because once you have these data collected in your interferogram, and then you sort of look at the, at least you do a Fourier transform across one axis, right?
So what we actually do, we do a lot of Fourier transforms in this process. You know, conceptually, we do a Fourier transform across one axis, but it's actually worse than that because, you know, in your other axis, a diffraction grating is roughly linear with wavelength.
Right.
But if you want to get it into frequency or to go to a time plot, you have to linearize it with regard to frequency. So you go from a wavelength axis to an inverse pixel axis. You do a Fourier interpolation there by zero padding. You bring it back now into a time axis, and you can go into a frequency axis from there. Okay. So there are manipulations that you have to do. That's from Lapetite and Joff, you know, circa 1993, where they started looking at the spectral interferometry and realized that that's how you had to approach this long before 2D spectroscopy. But we do a lot of those sorts of manipulations. So conceptually, we do one Fourier transform, but in practice, we exercise our Fourier transform algorithm
multiple times.
Quite a bit.
Right. So so here's the thing. So when somebody starts up with such a complex setup, is there any kind of tip you would like to give in terms of sort of utilizing certain methods so that the data that we see can be interpreted correctly? See, there could be other problems as you get to the 2D map. So
yeah, so you know, you're absolutely right. And so what we typically do is we take a sample that people have looked at a lot, like Nile blue. Right. Something where we know very well what the timescales are. There's only one transition to think about. It will start out inhomogeneous, and then based on solvent rearrangement, it will become homogeneous. And we look at something like that to make sure that we have the right pattern. The other thing that I always look at is the noise. So you want to make sure that you are not filtering or apodizing or something in a way that it changes the line shapes. And so looking at the statistical independence of points as you drill down to the noise, which often causes you know, now where we might have noise of, in one case with grapes, 10,000 to 1, you have to really dive pretty far down, but you need to see that noise spectrum too, to understand in a two-dimensional plot, the spatial coherence in some sense of that, to know if you're just seeing like big blobs or you see lots of little random things. And that tells you a lot about your apodization. The other thing that you can do is you can take fake data. I mean, nothing I presented is fake data, please. But you take a sine wave in 2 dimensions that looks like a checkerboard.
Right. It
should give you the narrowest possible peak you're going to see based on your spectrum. Make sure that you get what you think you're going to get. So put in an 800 nanometer by 800 nanometer sine wave, and get that right checkerboard, and make sure that you get some peak back at 800. If it shows up at 750, go back to work. Move it around, make sure that this works, make sure that you're not doing something a little bit strange.
Right.
And so, not only do you take data in from your spectrometer, you take in fake data that something that's just basically a delta function in frequency space, or a delta function in time, and make sure you know what that looks like in frequency space. And so you take some of these things where you have intuition. You can do a Lorentz line. There are lots of ways to kind of create fake data and see. And so we often will bootstrap our algorithms that way.
That's
please don't get me wrong. The data I showed you isn't fake. It's just how you test, it's how you test your analysis script to make sure that if you have a signal where you have intuition on what it should look like, that it gives you what you expect. And between comparing that to molecules that you understand, you can very quickly tell where the errors are. And we have had multiple students code it independently and run these checks and make sure they agree on the same data set. And over the years, that becomes quite easy because it's a good way to teach a new student how to interpret the data. Is write your own analysis code, and you see all the ways it can go wrong, but they really learn what's going on. But then you also, as a professor, see that it ultimately agrees with what you had before, and that's always very reassuring.
Okay, great. Thanks for those two questions, answer to the questions. And I would like to then, Satish, if you have any.
No, I think we have enough. It's a time to thank Greg once again. It was wonderful. I think we really thoroughly enjoyed. And thank you for your time and patience. I think you have really walked through very basics of that 2D spectroscopy. That was such a great treat to watch, actually. Like a person like me as a synthetic chemist, learn so much in-depth spectroscopy was a really treat for me. Thank you very much. That's what I want to say.
Yeah,
thank you so much for the invitation. It's been great fun.
Yeah, thank you, Greg. And we would love if you could come to India at any point and spend some time in Mumbai and Bangalore, these two institutes, as well as other places, of course. But
I would love that. That would be great fun. I've only been to India once before, and it was a fantastic time. I would look forward to visiting farther north.
Right, thank you. And I see Indranil Ghosh has joined you. He was one of the students from NICER, Bhubaneswar. I met him actually in one of my visits. Hi, Indranil.
Hi.
Hi. You remember me, right? We had the NMR.
Yeah, of course.
Okay. Yeah. Okay. So we also offered him for a graduate student in TIFR, but of course he joined U Chicago. So, okay, so.
We are very pleased to have him. We love getting fantastic students, and we are seeing so many strong students come out of India these days. It's just wonderful. And I would love to take more Indranils or Anshus or Viveks. So I mean, like this, we see a lot of intellectual strength coming out, and it's a function of the training. You guys provide a fantastic training opportunity. The research coming out of India is phenomenal now, and it's a great opportunity. I mean, it's the challenge now is convincing people not to stay. Which is great. I mean, this is the way science should advance. And it's wonderful to see people like Anshu coming back too.
Yes,
there's exciting stuff there.
Vivek, Anshu, all these people, they really enriched us. So that's
and us for that matter. No, I remember Anshu very clearly when I came as a young professor and seeing him and thinking, that's the kind of student I want. I didn't have him, of course. He worked with me. But I can take no credit for his brilliance, but I was jealous.
No, but we want that once Indranil and other kinds of students get trained in labs like yours, we hope that they can practice spectroscopy in their own labs and hopefully one day come up with new discoveries. And that
I am very confident that Indranil and others will be superstars in this regard, and we will all be competing for their attention at the time.
That's great. Thank you, Greg. Thank you very much. We are very appreciative of your gesture of being here, addressing difficult questions. So the point that you are at, with the vantage point you look at the field, we are asking probably hard questions, both hitting at, is this real? Is this true? Is this true? Every time we have that in our mind, and you've answered it with a very open mind. So thank you very much for doing that.
Thank you very much. These are the right questions to ask. This is why it's fun. Thank you. I really appreciate the opportunity. This has been great.
Thank you.
Bye-bye.
Thank you, guys. Thank you all for coming through, and we let him sleep today. Right. Okay. Thank you.
Bye-bye.
Good night. Good morning.